Hi everyone, welcome to the course on solid state. In previously, we have completed the solution chapter. Now we will move to the solid state, the very first chapter in second PU chemistry. Okay, so this chapter is also very important from the exam point of view. You will get one or two questions from this solid state chapter also in Karnataka CET, NEET or JEE. Now let us, before solving the questions based on solid state, first we will focus on some theory part that you have already learnt in regular classes. The first, as you already know, the solids, they exhibit certain characteristics, and those characteristics are they have definite mass, volume and shape. And the solids, in solids the intermolecular forces are very strong and they have high density, and the constituent particles are present at fixed positions and can oscillate only about their mean position. Okay, so these are all certain characteristics of solids. Now these solids, based upon the nature of order of arrangement of particles, they are classified into crystalline solids and amorphous solids. So how the particles are arranged in solid, a given solid, based on that the crystalline solids and amorphous solids are classified. So what are crystalline solids and what are amorphous solids? Let's see the difference between these kinds of solids. So the crystalline solids, as you observe, in crystalline solids there is a regular internal arrangement of particles. So the order of arrangement of particle in crystalline solids is definite or regular. That means they have definite geometry and arrangement of particles are periodic in nature. And in amorphous solids there is a irregular internal arrangement of particles. That means random arrangement of particles will be observed in case of amorphous solids. And crystalline solids, they have very sharp melting point, but amorphous solids, they melt over a range of temperature. That means as the crystalline solids have the particular melting point, we can mention the exact melting point of crystalline solids. But in case of amorphous solids, we cannot get the exact melting point of a solid. Instead of that, we can mention the range, that is the melting point is around about 500 to 520 Kelvin and 1000 to 1100 Kelvin. So in a range they will melt, and hence they don't have sharp melting point, okay, but melts over a range of temperature. And crystalline solids regarded as true solids, and amorphous solids regarded as supercooled liquids or pseudo solids. That means the amorphous solids, they shows the property of solids, but due to their ability to flow like liquids, they are considered as pseudo solids. The crystalline solids undergo regular cut. That means upon cleavage, the crystalline solids gives definite planes, pieces having definite planes, but amorphous solids upon cleavage, they won't give the pieces having definite planes. They will gives the pieces which are having irregular surfaces. The crystalline solids are anisotropic. Anisotropic means the physical properties values are different in different directions, just like thermal conductivity, electrical conductivity, okay, refractive index. All these values will differ when they are measured along different directions in case of crystalline solids. And amorphous solids, they are isotropic in nature. Isotropic means the physical properties values are same in all directions. They give same value if you measure in any direction in that crystal. And crystalline solids exhibit long range order and amorphous solids exhibit short range order. Long range order means the periodic repetition of arrangement of particles can be observed for a large extent. But in case of amorphous solids, the regular periodic arrangement or repetition of particles is observed for short distances only. Hence, amorphous solids considered to exhibit short range order, and crystalline solids are said to exhibit long range order. So these are certain differences between crystalline solids and amorphous solids. Okay, crystalline solids, examples for crystalline solids are salts like NaCl, KCl. Okay, such kind of salts are example for crystalline solids. And for amorphous solids, the examples are like rubber, silicone rubber. Okay, so these are glass, all those are examples for amorphous solids. One of the important example of amorphous solids is silicon. So that is used mainly in conversion of the light energy into electrical energy. Means that is used in a device known as solar cell or photovoltaic cell. Okay, in that device we will use the silicone rubber. Okay, so these are certain differences between and as well as characteristics of crystalline solids and amorphous solids. Next, based on binding forces, crystalline solids are further classified as follows. Okay, so I have already the characteristics of crystalline and amorphous solids. Now the crystalline solids, again they are further classified into different types based upon the binding forces present between them. Okay, so in crystalline solids, the constituent particles either may atoms or molecules or ions. Okay, based on that as well as on nature of binding force, they are classified into these following types. The first type of classification is based on atomic crystalline solids. That means the constituent particles are atoms here and the binding forces between them are London force or dispersion forces. The properties are soft, very low melting point, poor thermal and electrical conductors. Examples are noble gases. Noble gases like helium, okay, neon, argon. All these are examples for the atomic solids. Most of the time they are included in molecular solids only. Okay, so here it is individually classified, that is atomic crystalline solids. Examples are noble gases. Next one is molecular solids. So molecular solids, here the constituent particles, that is unit particles, they are maybe polar molecules or non-polar molecules. Okay, and based on that only molecular solids are classified into polar molecular solids and non-polar molecular solids, as well as hydrogen bonded molecular solids that you have already learned. And the nature of binding forces are van der Waals forces. They may be London force, dipole-dipole forces or hydrogen bonds. And properties, they are fairly soft, low to moderately high melting points, poor thermal and electrical conductors. Examples are dry ice, solid methane, etc. Solid hydrogen, solid iodine. All these are examples for molecular solids. The next type of crystalline solid is ionic solid or ionic crystal. And here the constituent particles are ions. They may be positive ions as well as negative ions. And the bonds present between them is ionic bonds, or there may be also, we can say, there is a presence of electrostatic force or coulombic force. So you can also remember these forces, electrostatic force or coulombic force are present between ions. Okay, so this is the another kind of another kind of crystalline solid. And the properties, when we look into the properties of these ionic solids, they are hard and brittle, high melting points, high heats of fusion, poor thermal and electrical conductors. Examples are NaCl and ZnS. So another point to remember here is these are pure thermal and electrical conductors, but this property is exhibited only if they are present in solid state. If they are present in aqueous solutions, or if they are present in molten state, then they are good conductors of electricity. They are good conductors. Okay, remember this. When they are present in solid state, they are bad conductors. But when they are present in aqueous solution or in molten state, then they are good conductors of electricity. Then the next one is covalent solids. Here the atoms are connected in covalent bond network. Hence these are also known as network solids. Covalent solids or network solids. Okay, or giant solids. These are having giant molecules. They with these single atoms, they are combined to form the large network structure. So hence they are network solids, or also they are called as giant molecules. And the binding force which is present between these atoms is covalent bonds. Hence they are called as covalent solids. And if you observe the properties, they are very hard, extremely hard, and extremely having high melting points and boiling points, and poor thermal and electrical conductors. Okay, examples are diamond, quartz, silicon. Remember, covalent solids have extremely hard in nature, and they are having extremely high melting point and boiling point among all these kinds of crystalline solids. Okay, so another thing here, these are poor thermal and electrical conductors, but exceptions are diamond. It is a very good thermal conductor. Okay, so good thermal conductor. Which one is diamond? And another one is exception from this character is graphite, which is a very good conductor of electricity. Good conductor of electricity. And you know the reason, because it consists of free pi electrons or valence electrons. So due to the presence of free pi electron or one free valence electron, these are good conductors of electricity. Which one? The graphite. Okay, then the next one is metallic solids. Metallic solids, here the constituent particles are metal ions or cations in electron cloud. They are also known as kernels. The positive ions or cations or metal ions, they are known as kernels. Okay, and the bond which is present between them is metallic bond. And these are the properties of the metallic solids, that is they are soft and to hard also, low to very high melting points, excellent thermal and electrical conductors, malleable and ductile. So this is the property, one of the important property exhibited by metallic solids. One is excellent thermal and electrical conductors, and another one is malleable and ductile. Malleable means they are They can be beatable, they can be converted into thin sheets, and ductile means they can be drawn into wires. So examples are all metallic elements such as copper, iron, zinc, etc. All the metallic elements are examples for metallic solids. So these are certain different types of crystalline solids. Remember their characteristics and examples as well as the binding forces which are present between the constituent particles. Now, the next part in the solid state is crystal systems. Up to this, you have discussed some general characteristics and behaviors of crystalline solids. Now, the next topic is crystal system. So, crystal system, here you come across lattices. Crystal lattice means the points or the particles that are regularly arranged in three-dimensional space. Such a type of system is said to be crystal lattice, and upon joining those points you will get a particular shape, and that system is known as crystal system. So there are totally 7 crystal systems are there, okay, and total number of Bravais lattices are 14. Okay, those 7 crystal systems are cubic, orthorhombic, tetragonal, monoclinic, triclinic, hexagonal, rhombohedral. These are the 7 crystal systems, and total number of Bravais lattices are 14. Those 14 are primitive, face centered, body centered. Okay, so if you combine all these things, you will get total 14 Bravais lattices, and these are the edge lengths A, B and C. Here you must know the meaning of one term, that is unit cell. Unit cell, it is the smallest portion of the crystal lattice, okay, and it gives the definite geometry of a particular crystal system. The shape of the unit cell represents the shape or geometry of the crystal system. Okay, unit cell is the smallest portion of the crystal lattice, and these unit cells are classified into 2 types. Those are primitive and non-primitive. Okay, these things you have already learned, primitive and non-primitive. So primitive means the particles are present only at the corners. Non-primitive means the particles are present at the corners as well as different parts of the unit cell. And in non-primitive cell only you can observe the body centered, face centered and end centered unit cells. Okay, and those constitutes Bravais lattices. In 7 crystal systems, 14 Bravais lattices can be found, and A, B, C are edge lengths, okay, and alpha, beta, gamma. You can hear A, B, G is mentioned. Instead of that, you can also consider as alpha, beta and gamma, that is equal to 90 degree. A means alpha, B means beta, G means gamma. Here we have not used a symbol. Instead of that, we have used the first letter of that symbol. A means alpha, B means beta, G means gamma. Okay, so remember these crystal angles and intercepts, that is the edge lengths. Okay, in cubic, what is the crystal angle? In orthorhombic, what is the crystal angle and intercepts? And tetragonal, how it is there? And what are the examples of those crystal systems? Okay, all these things you need to remember. Okay, especially the intercepts, that is the edge length and crystal angles for these crystal systems. Okay, the most symmetric crystal system among these 7 is cubic, because all the edge lengths are equal and all the angles are also equal. And the most unsymmetric one is triclinic crystal system, because all edge lengths are different and all angles are also different. Okay. Next, number of atoms in unit cells. As I have already told you, there are different types of unit cells. Just remember what are the number of particles or atoms in cubic unit cells. Okay, there are 7 crystal systems, but we concentrate only on cubic crystal system. So in primitive cubic unit cell, okay, the number of particles is 1, because from each corner, how much portion belongs to the unit cell? 1/8 portion. Okay, and this part, okay, this is 1/8, 1/8. So if you take the 1/8 portion from one corner, there are totally how many corners? 8 corners are there. So 1/8 into 8 will give 1. And number of atoms in faces is 0. Number of body center atoms at body center is 0. Total number of atoms, so it becomes 1. Okay, that is from corners. And in body centered unit cell, 8 corners are there. So 1/8 into 8, 1 atom is there at the corners. And on faces, no atom is there. At the body center, one whole atom is there. So 1 plus 1, that is equal to 2. So the total number of atoms in body centered cubic unit cell, or you can also say it as BCC, okay, is 2. And in face centered cubic or cubic closed packed unit cells, okay, you can call it as FCC or CCP. So here the number of atoms at corners is 1, and the number of atoms in faces is 3, and number of atoms at body center is 0. So the total number of atoms in FCC or CCP is 4. So these are the number of particles which are present in the unit cell, and remember these number of particles because these are very important. They can ask directly, or they are used in the problems. While solving the problems, they just mention the BCC, FCC or SCC. Based upon that, you have to take the number of atoms. Okay. Next, packing efficiency. So the packing efficiency means, as you know, in solids, the particles are arranged closely. Okay, close packed arrangement is observed in case of solids, where maximum number of particles are present in a minimum space, and there how much that solid is packed efficiently by the atoms or any constituent particle, that can be calculated by using the formula of packing efficiency. Okay, this is simply the ratio of volume occupied by all the atoms present in the unit cell divided by total volume of unit cell into 100. Okay, if you use this formula, then you can easily get the packing efficiency of a given crystal system. Okay, so here are the some structures, closed structures have been given, and what is the packing efficiency of those systems. So in HCP and CCP or FCC. Okay, so HCP, CCP or FCC. In this, number of atoms per unit cell is 4, and the relationship between edge length A and radius R, it is given by R is equal to A by 2 root 2. Okay, and then here packing efficiency is 74%. Remember, HCP means hexagonal close packed structure, and here the number of atoms or particles is 6. In CCP or FCC, already in previous slide you have seen, it is the number of atoms are 4. Both are same, CCP and FCC. HCP, it is different structure, and here the number of atoms is 6. But the packing efficiency in HCP is also same, that is 74%. And in BCC, the number of atoms is 2 and the relation between radius and edge length is given by this formula, R is equal to root 3 divided by 4 into A, and packing efficiency is 60%, 68%. Simple cubic lattice SCC, number of atoms is 1 and the relation is given by R is equal to A by 2 and the packing efficiency is 52.4%. Among these structures, the most efficiently packed structure is CCP or FCC or HCP because their packing efficiency is 74%. Next, density of the crystal lattice. So, as you know, the atoms are present and they are closely arranged. Then, what is the density of that crystal lattice? Because all the solids will not have the same density, and you need to find the density. What is the density of those crystals? And this can be obtained by the formula D is equal to Z into M divided by A cube into Na. This is the formula that you know. So remember this only. Here also it is same. R means here that represents density. So Z is number of atoms, M means molar mass, V means volume of unit cells, and volume of unit cells is calculated by A cube, and Na means Avogadro's number. So remember, Z number of atoms, M means molar mass of a given solid, and A means edge length, okay, and A cube means volume, and Na is Avogadro's number, that is 6.022 into 10 raised to 23 gram per mole, or you can, in some books they can also mention 6.023. So you can take any of the value if they have given. Okay. Next, octahedral and tetrahedral voids. When the close packing arrangement takes place, certain voids are formed in the crystal lattice, and voids are nothing but empty spaces present inside the unit cell and between the atoms. Empty spaces between the particles is considered as voids. The number of effective atoms present in unit cell. See here, number of octahedral voids, if you denote it as N, and number of effective atoms present in the unit cell is also N. Okay, both are equal. Number of octahedral voids and number of atoms, N is equal to N. So if they want to find how many tetrahedral voids are formed, then number of tetrahedral voids is twice that of the number of atoms, that is 2 into N. So the number of tetrahedral voids is equal to 2 into N. So number of octahedral voids is N and number of tetrahedral voids is equal to 2N. If 10 particles are present, number of octahedral voids formed is 10. Number of tetrahedral voids formed is 20. So twice that of the number of particles in case of tetrahedral voids. Okay. Next, coordination numbers and radius ratio. The coordination numbers means the number of nearest neighboring atoms to the constituent particle or particular atom. So if I consider this one as an atom, here the neighboring atoms, number of neighboring atoms is 2. Okay, exactly at the adjacent sides there are 2 particles. So coordination number is 2. If you consider this arrangement, if I say what is the coordination number, okay, here if you consider this constituent particle, how many neighboring atoms are there? 1, 2, 3 and 4. So the coordination number is 4. Hence, the coordination number can be defined as number of nearest neighboring atoms surrounded to each atom. And radius ratio means it is the ratio of radius of cation to the radius of anion. So this radius ratio, it helps to determine whether the particular particle will fit into the void or not. If there is one particle and this is the void, okay, and in this void every particle will not fix, okay, only certain particles will enter into that void, and to enter or fix into that void they must have certain size, okay, and that can be calculated by the radius ratio, okay, which helps to determine whether the particular particle fix or enter into that void or not, okay. Now here there are certain examples. Coordination numbers. If the geometry is linear, then coordination number is 2. Linear means they are simply arranged like this, closed arrangement, and they are linear. At such condition coordination number is 2. And radius ratio, remember these values, x is less than 0.155, okay, and example is BEF2. Third, next one, if the coordination number is 3, that means the geometry is planar triangle, and here the radius ratio must be in the range 0.155 less than or equal to x less than 0.225, okay. If it has 0.155 or less than 0.225, then it has the coordination number 3 and its geometry is planar triangle. Without any doubt, you can directly say the geometry of the given crystal is planar triangle. If I have given the radius ratio of one of the crystal is 0.166, then what is the geometry? Planar triangle. What is the coordination number? 3, because it lies in this range, okay. By using that you can directly say, and the example is AlCl3. Next, if the structure or geometry is tetrahedron and the coordination number is 4, then the radius ratio is 0.225 to 0.414, and the example is ZNS. Next, the coordination number 4, square planar structure, then the radius ratio is 0.414 to 0.732. Example is PTCl4. And the coordination number is 6, structure is octahedron, and the range is 0.414 to 0.732, okay. Both are having the same radius ratio, that is example is NaCl. Only the structure is different, radius ratio will be same. And if the body centered cubic, then the coordination number is 8 and the range is 0.73 to 0.999. Example is cesium chloride. So remember these radius ratio ranges, okay, and the geometry and the coordination number with example, okay. So important one, this one is also, remember this table. Now classification of ionic structures. So how they are classified? Here you know ionic structures means they are ionic crystals and the constituent atoms are ions, and based upon their structure, okay, the different ionic structure, ions have different ionic crystals have different ionic structures, and some of the important are structures. Rock salt structure, where the anion forms FCC units and cations occupy octahedral voids. Z is equal to 4, that is number of atoms is 4 and the coordination number is 6. Remember these things carefully because these can be asked in examination. These among these structures at least one question may come, okay. And next, zinc blende structure. Here anion forms FCC units and cations occupy alternate tetrahedral voids. Z is equal to 4 and the coordination number is also 4. The number of atoms is 4 and coordination number is also 4, okay. If the ionic crystal has fluoride structure. That means cation forms FCC units and anions occupy tetrahedral oids. And number of atoms is 4. Coordination number of anion is equal to 4. And coordination number of cation is equal to 8. See here, the coordination number for anion is 4, but the coordination number for cation is 8 in case of fluoride structures. And example are calcium fluoride, uranium oxide and thorium oxide. Okay. Next, antifluoride structure. Antifluoride structure means the oxide ions are face centered and metal ions occupy all the tetrahedral oids. And examples are Na2O, K2O and Rb2O. Remember, if the compound is of type of AB2, then the structure of ion crystal is AB2. And if the formula of the compound is A2B, then it is an antifluoride structure. Okay, AB2 fluoride structure, A2B antifluoride structure. And examples. Okay, now cesium halide structure, cesium bromide, cesium chloride, all those things. Okay, how the particles or ions are arranged. Halide ions are primitive cubic, while the metal ion occupies the center of the unit cell. Z is equal to 2. Number of atoms is 2 and coordination number is 8. Okay, it simply form a BCC type structure. Next, perovskite structure. One of the cation is bivalent and other is tetravalent. The bivalent ions are present in primitive cubic lattice with oxide ions on the center of all the 6 square faces. The tetravalent cation is in the center of the unit cell occupying octahedral void. Examples are calcium, titanium oxide, barium titanium oxide. And spinal structure and inverse spinal structures. In spinal, M plus 2, M2 plus 3, O4, where M plus 2 is present in 1/8 of the tetrahedral oids in FCC lattice of oxide ions, and M plus 3 ions are present in the half of the octahedral oids. M plus 2 is usually Mg, Fe, Co, Ni, Zn. Okay. So up to this it is sufficient. So remember the examples. So these are the ionic structures. Some important ionic structures. Okay. Remember the arrangement and examples of those type of structures. Next, defects in crystal. As you know, there is a regular arrangement of particles in crystal, but there are certain defects in the crystal. That means at some point the arrangement of particles is not regular. There may be presence of empty space, or there may be absence of 1 or 2 particles in the particular arrangement of particles. So due to that, the defects is arised in the crystals. That deviation in the arrangement of particles is said to be crystal defect. And there are different types of crystal defects, and here I have discussed some important defects only. Those are stoichiometric defects, okay, and non-stoichiometric defects. These two things I have discussed here. Okay, so first we will see stoichiometric defects. First one is Schottky defects. Here the sum of the lattice points in a crystal are unoccupied. That means there is a missing of equal number of anions and cations. Anions and cations are missing. If 2 cations are missed, there will be missing of 2 anions also. Equal missing of cations and anions takes place. So you can say it is a type of vacancy defect, and appears in ionic compounds in which anions and cations are of nearly same size. Okay, this kind of defect is found where the anions and cations size are same in the crystals, and decreases the density of lattice, because as the ions are removed but the space is that much only, due to that the density of the crystal will decreases. Examples are NaCl and KCl. And the next one is Frenkel defects. Ion dislocates from its position and occupies an interstitial position between the lattice points. So if you observe, it is the arrangement of particles, and here you will see the interstitial space, and the ions will occupy that interstitial space. From original side to interstitial space they will move, and hence it is also known as dislocation defect, and appears in crystals which the negative ions are much larger than positive ions. So the positive ions can easily accommodate that interstitial site. Does not affect density of the crystal because the ions are not removed here. They just dislocated from one position to another position inside the crystal. And examples are AgBr and ZnS. Next, non-stoichiometric defects. In these defects there are two types: metal excess defect and metal deficiency defect. The metal excess defect occurs due to anionic vacancies or presence of extra cation. And F centers, here it is one of the important thing. These are the hole produced due to absence of anion which is occupied by an electron, and this results, the presence of an electron results in the colors of the crystal. Okay, crystal becomes colored because of presence of this F center. Okay, it is also known as coloring center, Farben center. F means Farben center, that means coloring center. And metal deficiency defect. Metal deficiency defect occurs due to variable valency of metals. When one of the positive ions is missing from its lattice site and the extra negative charge is balanced by some nearby metal ion acquiring two charges instead of one. So these are the defects that you have studied. Okay, just I have glanced all these defects, important for the examination. And the classification of solids on the basis of electrical conductivity. As you know, the rubber is solid and iron is also present in solid state. But iron is a good conductor and rubber is a bad conductor. If you consider the silicon, they are neither good conductors of electricity or bad conductors of electricity. Means they will show intermediate property between the conductivities of conductors and insulators. So this is the information which is given table based on their electrical conductivity. Okay, so based on conductivity they are classified into conductors, insulators and semiconductors. Conductors are good of electrical conductivity and insulators does not conduct the electricity. Semiconductors partially conducts the electricity. And this variation in the conductivity of solids can be explained on the basis of valence band theory, okay, or simply band theory. So here there are two bands, valence band and conduction band. Here you can see, and these are separated by certain energy difference, that is forbidden zone. Okay, in case of conductors there is no forbidden gap or energy gap. Okay, the ions or electrons can easily accommodate in conduction band and they can move and conduct the electricity. And in case of insulators there is a large forbidden zone. Okay, due to presence of large forbidden zone, the electrons in valence band cannot able to jump to the conduction band, hence they will not conduct the electricity. But in case of semiconductors, the difference is small. There is a small energy gap. So some of the ions or electrons can jump into the conduction band and conduct the electricity partially. And here are the certain things, important notes. The electricity produced on heating a polar crystal is called pyroelectricity. Okay, by heating a crystal we can able to produce electricity in some crystals, and that kind of electricity is known as pyroelectricity. And when mechanical stress is applied on polar crystals, electricity produced due to displacement of ions is called piezoelectricity. Okay, piezo means pressure. So mechanical stress means by applying pressure, if we produce electricity, then it is known as piezoelectricity. Next, semiconductors. So here the semiconductors, these partially conduct the electricity, but their conductivity does not have much importance in day-to-day life. So in order to increase their conductivity, we will add certain impurities into that semiconductor, and that process of addition of impurities to enhance the conductivity of semiconductors is known as doping. Okay, so here simply observe electronic conductors having the electrical conductivity in the range of 10 raised to 4 to 10 raised to 7 are known as semiconductors. Okay, examples are silicon, germanium, etc. Intrinsic semiconductors, pure substances that are semiconductors are known as intrinsic semiconductors. Means no impurities are added into these semiconductors. And extrinsic semiconductors, to enhance the conductivity, we will add certain impurities, that is known as doping, and conductivity is increased. And example, here we can add phosphorus, arsenic, barium, etc., boron, aluminum, gallium, etc. And here by addition of doping, addition of impurities, we can form different types of semiconductors. Those are N-type semiconductors and P-type semiconductors. And N-type semiconductors are formed when silicon doped with 15 group elements. That is, they must be pentavalent. Okay, pentavalent means 5 valence electrons they must have. Then we will get N-type semiconductors, and conductivity is due to negative charge, or you can say electrons. The conductivity is due to electrons. And in P-type semiconductors, these obtained by addition of impurities which belongs to 13th group, okay, such as gallium. And here the conductivity is due to presence of positive poles. Next, magnetic properties of solids. So as you have studied the defects and electrical properties of solids, some general characteristics of solids, and now magnetic properties of solids. As you know, some of the solids will attract towards the magnet. Okay, in presence of magnetic field they will behave differently, and based on that they are classified into diamagnetic, paramagnetic, ferromagnetic, antiferromagnetic, and ferrimagnetic substances. So we will see one by one. Diamagnetic substances, these are weakly repelled by the magnetic field and do not have any unpaired electron. Example, titanium oxide, vanadium oxide, benzene, NaCl, etc. Okay, they does not consist of any unpaired electron. Okay, and in paramagnetic substance they contain unpaired electron or odd number of electrons, and hence they will weakly attracted by magnetic field and lose magnetism in absence of magnetic field. If the magnet is removed, then they will lose their magnetic property. Examples are O2, Cu plus 2, Fe plus 3, etc. Then third one, ferromagnetic substances. These are the substances which are strongly attracted by magnetic field and show permanent magnetism even in the absence of magnetic field. So if you remove the magnetic field, then also they behave as magnets. So they are strongly attracted by magnetic field. and examples are Fe, Co and Ne. Okay. Antiferromagnetic substances. These substances have net magnetic moment 0 due to compensatory alignment of magnetic moments. So here we will call domains. Okay, domains are the group of ions and they are arranged in one direction spontaneously. So if they are arranged spontaneously along the direction of magnetic field, then they are said to be ferromagnetic substances. The arrangement of those domains can be represented like this. And in antiferromagnetic substances, the net magnetic moment is 0. That means the alignment of those domains is in compensatory way, such that the net magnetic moment becomes 0. And the next one is ferrimagnetic substance. These substances have a net dipole moment due to unequal parallel and anti-parallel alignment of magnetic moments. So here the net magnetic moment is there due to the parallel and anti-parallel alignment of the domains, and you can represent those arrangements in this manner. So in alternate manner and in unequal parallel and anti-parallel alignment is observed. An example is Fe3O4 and ferrites, etc. So these are certain types of solid substances which are classified on the basis of magnetic properties of solids. Okay, so in the next video we will solve problems based on the solid state. Okay students, now we will solve the MCQs based on solid state. The first one is, which of the following is not a characteristic property of solids? So option A, intermolecular distances are short, intermolecular forces are weak, constituent particles have fixed positions, solids oscillate about their mean position. So if you know the characteristic property of solids very well, then you can easily answer to this question. Okay, so what are the characteristic properties of solids? They are having definite mass, volume and shape. The intermolecular forces are strong and the intermolecular distances are short. Constituent particles have fixed positions. Solids oscillate about their mean positions. So these are all the characteristic property of solids. Among these four options, the option B, it gives intermolecular forces are weak. Okay, but as you know, the solids, the particles in solids are having strong intermolecular forces and hence they have definite mass, volume and shape. Okay, so the option B, this statement is the wrong statement. Okay, so among these four, option B shows that this is not a characteristic of solids. Okay, so option B is the right one. Now next question. The most crystals show good cleavage because their atoms, ions or molecules are weakly bonded, strongly bonded together, spherically symmetrical, arranged in planes. As you know, crystals, they upon cleavage or upon cutting, they give the regular shaped pieces having definite planes, because the atoms or ions among the crystals, in crystals, you know, the atoms, ions or molecules in crystals upon cleavage give definite planes. It is because those constituent particles are arranged in planes and hence they give the regular shaped pieces upon cleavage having definite planes. Hence they show good cleavage because the particles are arranged in planes. So the option D is the right one. So third one, crystalline solids are anisotropic in nature. What is the meaning of anisotropic in the given statement? So you already know anisotropy. It means the physical properties are different in different directions. Now in given statement, which one is right, that you have to see. So first one, a regular pattern of arrangement of particles which repeats itself periodically over the entire crystal. Different values of some physical properties are shown when measured along different directions in the same crystal. Okay, so no need to read other options because the option B only gives the definition of anisotropic. And if you see the option D, what they have given, same values of sum of physical properties are shown measured along different directions in the same crystals. So this is isotropic definition, but they asked for anisotropic. So the option B is the right answer. Next, fourth one, a crystalline solid changes abruptly from solid to liquid when heated, has no definite melting point, undergoes deformation of its geometry easily. D has an irregular three-dimensional arrangements. So among this, which one is right? No doubt, option A, changes abruptly from solid to liquid when heated. This one is the right one. Has no definite melting point? No, it is the property of amorphous solids. Undergo deformation of its geometry easily? No, because the particles are strongly held and regularly arranged. Has an irregular? No, it has regular arrangement of three-dimensional arrangements. So the option A is the right one. That is the characteristic of crystalline solid. So the fifth one, which of the following is not a characteristic of a crystalline solid? Option A, definite and characteristic heat of fusion, isotropic nature, regular periodically repeated pattern of arrangement of constituent particles in the entire crystal. Option D, a true solid. Which is not a characteristic of crystalline solid here? Option A, option C, option D. All these are right on. And option B, the isotropic nature, because it is shown by amorphous solids. So this statement or this characteristic is not a characteristic of crystalline solid. It is a characteristic of amorphous solid. So option B is the right one. Sixth one, which of the following is not a crystalline solid? So if you know the examples of amorphous and crystalline solids, you can easily answer for this. KCl, potassium chloride, is a crystalline solid. Cesium chloride is also a crystalline solid. Rhombic sulfur, rhombic means it has definite shape. That means it is a crystalline solid. Glass, it is an example of amorphous solid because it has ability to flow. So that's why it is known as supercooled liquid or pseudo solid. So the option C is the right. It is not a crystalline solid. Seventh one, which of the following amorphous solid is used as photovoltaic material for conversion of sunlight into electricity? So already while discussing the synopsis, I have told you the one of the important example of amorphous solid is silicon, which is used in photovoltaic material for conversion of sunlight into electricity. Quartz glass, quartz, both A and B, they are not used in photovoltaic material. So option C is the right one. Eighth one, iodine molecules are held in crystal lattice by London forces, dipole-dipole interactions, covalent bonds, coulombic forces. See, iodine, that means I, it is atomolecule. So both they are having same electronegativities because they are same atoms. So when they are having same electronegativities, then the weak bond is formed between them, and that one is known as a non-polar molecule. I2 is a non-polar molecule because these I2s are having same electronegativities, and hence you can observe the weak London forces between the I2 molecules. If you consider this one and this one as a two molecule, then in between these two molecules you will see the weak forces, that is London force or dispersion force, because it is a non-polar molecule. For non-polar molecules you will observe London force. Non-polar and noble gases, okay, they have London forces. Dipole-dipole interactions, HCl is an example of dipole-dipole interaction. Covalent bonds, you can observe the different examples like diamond, graphite, diamond, graphite, all those things. Coulombic forces, NaCl, KCl, these are examples of Coulombic forces. Okay, so in this question iodine molecules are held by London forces. Okay, so the option A is the right one, option A. Next, 9th one, graphite is a good conductor of electricity due to the presence of A, lone pair of electrons, B, free valence electrons, C, cations, D, anions. As you know, graphite, it consists of delocalized p electrons, that is free valence electrons, and hence it is a good conductor of electricity. Option D is the right one. 10th one, how many three-dimensional crystal lattices are possible? There are 7 crystal systems. So there are 7 crystal systems and 14 three-dimensional crystal lattices are possible. Those are said to be Bravais lattice. Bravais lattices. Okay. So there are 14. So the option C is the right one. 11th one, in face-centered cubic lattice, a unit cell is shared equally by how many unit cells? 11th one, in face-centered cubic lattice, a unit cell is shared equally by how many unit cells? So here in each face, half portion belongs to the unit cell. Okay, so there are totally 6 faces. It is again shared with other unit cells. Okay, there are totally 6 unit cells, that is option C. It will share because 6 faces are there. So 6 faces means it is surrounded by 6 unit cells, and half will shared with other unit cell. But they don't ask number of atoms, but they asked for unit cell. How many unit cells are surrounded, or with how many unit cells it will share. Okay, so that a face-centered unit cell is shared equally by 6 unit cells. So option C is the right one. Next, 12th one, the number of atoms per unit cell of BCC structure is. In synopsis, you have already studied it. The number of atoms in BCC is 2. Okay, that is 1/8 portion from 8 corners, that gives 1, and 1 atom at the center. So 1 plus 1, that gives 2 atoms. Okay, there are totally 2 atoms per unit cell of BCC structure. Option B. Next, 13th, the molten zinc is converted into solid state. It acquires HCP structure. The number of nearest neighbors of zinc will be. So in close packed structure, when it forms HCP, it will form 3-dimensional HCP structure. And the coordination, the number of nearest neighbors of zinc, that means this number of nearest neighbors indicates coordination number. Okay, the coordination number is 12 for HCP. So the number of nearest neighbors of zinc will be option B, that is 12. Next, 14th one, the number of octahedral oids present in a lattice is A. The number of closed packed particles, the number of tetrahedral oids generated is B. The number of closed packed particles. A equal B half, B A twice, B equal C A twice, B half, D A equal B twice. So what they have given, simply write down number of octahedral oids present in lattice is A. Octahedral oids. How many octahedral oids are there? A. The number of close packed particles, the number of tetrahedral oids generated is B. Okay. So number of tetrahedral oids generated is B. The number of closed packed particles. So how many closed packed particles are there? If the octahedral oids, number of octahedral oids is A and tetrahedral oids is B. As you know, the number of octahedral oids, that is equal to number of particles. So if the number of particles is n, the number of octahedral oids formed is also n, and number of tetrahedral oids formed is 2n. So the number of closed packed particles, that is here A equal B half. A means octahedral oids, B means the number of tetrahedral oids. That is not right because it is double that of the A. So this one is wrong. A twice B equal. No, because tetrahedral oids B, it is not equal to the number of particles. So this one is also wrong. A twice B half. As you know, B is always twice and A is equal to the number of particles. So option C is also wrong. A is equal, B is twice. So A, number of tetrahedral oids formed is equal to the number of close packed particles, and B is twice that of the number of particles, that is 2n. Okay, so here you will get the answer as option D, because number of octahedral oids formed is always equal to the number of particles, and number of tetrahedral oids formed is twice the number of particles. So option D. Next, 15th one, the arrangement ABC is referred to as octahedral close packing, hexagonal close packing, tetrahedral close packing, cubic close packing. Okay, so as you already know, in hexagonal close packing, you have learned two types of close packing: hexagonal close packing, cubic close packing in 3-dimensional. So in hexagonal close packing, you will observe AB type, and in cubic close packing, you will observe ABC type of arrangement. So option D, here you will observe, that is CCP or FCC. Arrangement is ABC and coordination number is 12, and here also the coordination number is 12 in HCP as well as in CCP, but the arrangement in HCP is AB, and in option D, that is in CCP, arrangement is ABC. The 16th one, the empty space in the body centered cubic lattice. Okay, how much empty space is there in BCC? First, you should know what is the packing efficiency of BCC. BCC, its packing efficiency is 68%, FCC 74%, SCC 52.4%. So they asked for BCC. Okay, 68% it is the packing efficiency. That means 68% has been completely packed with particles. and remaining thing is empty space. So they asked the empty space. So how much is filled? 68% is filled. So empty space, that you need to know, that you have to calculate. How you will calculate? Simply 100 minus 68 is filled. In 100%, 68% is filled. How much it remains? 32%. So 32% of the body centered cubic lattice is empty. So the option D is the right one. Here we will stop. In next video we will discuss further questions on solid state.